Welcome back to BE544. In Lecture 1, we established the foundational principles of histopathology from specimen collection to microscopic diagnosis. Today, in Lecture 2, we transition into the digital domain. We will explore how traditional glass slides are converted into high-resolution digital images, which are the technologies that enable this transformation and the implications for AI-driven analysis. This lectures sets the stage for understanding data acquisition, which is the first critical step in any computational pathology pipeline. Digital histopathology refers to the process of converting conventional glass microscope slides into high-resolution digital images that can be viewed, analyzed, and stored on a computer system. Unlike traditional microscopy, where only a small field of view is visible at any moment, digital histopathology captures the entire tissue section in a single, navigable file. This digitization enables remote consultation, telepathology, longitudinal archival, and most importantly for this course, the application of computer-assisted diagnostic tools, including machine learning and deep learning algorithms. The shift from analog to digital is not merely technological, it represents a paradigm change in how pathologists interact with tissue data. At the heart of digital histopathology lies a whole slide scanner, which is a specialized instrument which is designed to automate high-fidelity image capture across the entire glass slide. These scanners integrate precision robotics, high-magnification optics, and advanced image processing to produce gigapixel-scale images. Critically, scanner performance digitally directly impacts downstream AI tasks where variations in focus, color fidelity, or stitching effects can introduce noise that confounds model training. Therefore, understanding scanner capabilities and limitations is essential for anyone developing or deploying AI in histopathology. And these are samples from the digital microscope, where each of them can take multiple slides and the scanner itself will scan one by one, or according to the scanner pipeline itself. Scanning parameters govern the quality and utility of the resulting digital image. Some key settings include magnification levels, and this is which determine the level of morphological detail captured. They can range from low bar overviews such as 10x for architectural assessment to high-power views such as 40x and 400x for nuclear and subnuclear analysis. Autofocus is a setting that ensures consistent sharpness across uneven tissue surfaces, and it's considered a common challenge in thick and folded sections. Third, stitching. And stitching here determine how multiple image tiles are seamlessly stitched together to create a complete digital representation of the slide. Poorly tuned parameters can lead to blurring, misalignment, or less of relevant features of the whole slide. For AI developers, these parameters define the input data distribution and thus must be accounted for during model design and validation. A whole slide image, or in short WSI, and also known as a virtual slide, is a complete digital representation of an entire histopathology slide. It preserves both spatial context and microscopic detail. Unlike static or traditional microscopy, whole slide images allow users to pan, zoom, and navigate the tissue as if using a physical microscope. They are generated by scanning the slide at multiple magnifications and stitching adjacent fields of view into a single high-resolution composite. Critically, whole slide images retain the same diagnostic information as their glass counterparts, making them suitable not only for primary diagnosis in some regulatory frameworks, but also as the foundational data source for AI algorithms in research and clinical deployment. Once the glass slide is scanned as a whole slide image, it comes with an enormous size. And due to their enormous size, which is exceeding, for example, 100K by 100K pixels, whole slide images cannot be stored or displayed as conventional images. Instead, they are organized using efficient multi-resolution schemes. The first one is pyramidal view, and this structures the image as a hierarchy of resolution levels like a pyramid, like here, where the base contains the full resolution data, while higher levels offer progressively downsampled versions. So in this example here, we have the base comes at 40x magnification, which is considered the full resolution data. It can be 400x or 100x according to the configuration and the scanner type and capabilities. And once you go from base to the top, you decrease the resolution. For example, here 40x and here is 10x and here is 1x. And these are downsampled versions from the base version or the full resolution data. This allows the viewers to load only the necessary tiles at the current zoom level, conserving memory and bandwidth. Alternatively, the tiled view, which divides the image into fixed size batches, for example 256 by 256 pixels, which are streamed dynamically during navigation. And both approaches enable interactive exploration of gigapixel images on standard hardware, which is a prerequisite for scalable AI workflows that process whole slide images batch by batch. So now we have the pyramidal view and tiled view. This is the pyramidal view and this is the tiled view. So this will be a portion of the whole slide images or a specific view, and each of them are tiles. So here we are dividing the whole slide images or a specific view into tiles. And once you navigate to any direction, for example to the right, more tiles will be loaded during that navigation. So whole slide images are stored in these two schemes, pyramidal view or tiled view, in a specific file formats, broadly categorized into two types. First, standard image formats, such as TIFF and JPEG, and those offer wide compatibility and support for lossless and lossy compression. However, they often lack native support for multi-resolution or even metadata. Second, vendor-specific formats, like SVS or NDPI, where those can be embedded with rich metadata such as a magnification, scanner model, staining protocol, and natively support the pyramidal storage. While these formats enhance the functionality, they may require specific software libraries such as OpenSlide for programmatic access. And for AI practitioners, formatted choice affects preprocessing complexity, storage efficiency, and interoperability across institutions, making it a key consideration in the dataset correlation step. So the idea is to obtain data during the data correlation step, such as bringing some physical class slides and scanning them or obtaining them from a private repository from a specific hospital or a community. But in the case that we couldn't do that, we can refer to other public repositories. Either ways, accessing to high-quality annotated whole slide images datasets is critical for training and validating AI models. One of the most valuable public resources is the TCIA, which is the Cancer Imaging Archive. It provides curated collections of cancer-related imaging data, including histopathology slides linked to clinical and genomic metadata. The TCIA supports reproducible research by offering standardized de-identified datasets across tumor types such as breast, lung, and prostate cancers. Utilizing such repositories enables researchers to develop generalizable models while adhering to ethical and regulatory standards. There are many other repositories and platforms that offer whole slide images other than the TCIA, such as Kaggle, which also can be used to obtain data for research and educational purposes. This video shows how to obtain the data from the TCIA. So you navigate to the website and click on the access the data, then search the histopathology. Then depending on the version of the view or the TCIA application, you need to select and filter the required data. For example, the cancer location, the data format. For example, here we select SVS and the protocol. Let's say that we are going to extract or get hematoxylin and eosine or H&E stains. So here we are filtering and targeting a specific type of data. After that, you will get a tabular format or a table like that, where you will get the different information such as the data format, the location of the whole slide images, the magnification level, the number of subjects in that collection. For example, here in the location, we have breast, skin, ovary, chest, and prostate. You can sort them by pressing on the location. And let's say that we need to select the HER2 for the breast cancer. So now you have two options, whether you view or download. If you press on view, you will be navigated to the collection. And here we have different slides or cases. You can press on a specific case to view its case or its whole slide image. Once you press, it's being loaded, and then you can navigate that image. You can pan, you can zoom. Also, you can download it by pressing on download. You will be navigated to the download link. You can download from here or according to the hosting website of the data. For example, we have here 4 elements that can be downloaded. Here we have the annotation and SVS files. Inside that folder, which is the SVS file folder, you can select specific cases to be downloaded. Here we have 273 patients and images, and this is the DOI of the dataset. You can get the DOI or that link and navigate to that link. It will be guided or transferred to the website of the data, and it's not mandatory to include the DOI, but just in case, here we have a summary of the dataset and the different metadata for the data, such as the size, it's 40 gigabytes, it's public and complete, and it contains 273 subjects, and it's for the human breast. And these are the other metadata and information about that dataset. So now you have learned how to navigate to the TCIA and how to obtain such data, whether by viewing or downloading. And let's assume now that we got data, whether it's private or public, from a public repository such as TCIA or Kaggle. Now we need to know about the applications. There are several powerful software platforms that enable the viewing, annotation, and analysis of the whole slide images, where each comes with unique strengths for AI development. The first is QPath, which is an open source tool that's widely used in academia. It supports deep learning, integration, cell detection, and tissue classification. Second, the ImageScope, which offers robust annotations and measurement tools compatible with SVS files. Also, there is Orbit Image Analysis that provides a comprehensive suite for quantitative pathology, including built-in machine learning modules for automated tumor detection and biomarker quantification. These applications not only facilitate human interpretation, but also serve as testbeds for prototyping and validating AI algorithms before clinical integration. And this concludes Lecture 2. Here we have now covered the end-to-end digitization pipeline from physical slide to structured digital asset, laying the groundwork for computational analysis. In Lecture 3, we will transition from theory to practice by introducing QPath, which is an open source platform widely used in digital pathology for viewing, annotating, and analyzing the whole slide images as mentioned. You will learn how to navigate the whole slide images, perform data segmentation, extract quantitative features, prepare data for AI pipelines, and many more.